Şöyle sayfaları göstereyim de. Okay, so all right, so we started with review of what we did last time. We defined last time tangent vector, and a tangent vector has two parts, a vector part and a point of application. And point of application means we just take the derivative of a function at that point. So our application is just actually taking directional derivatives. And we stated this theorem last time. And then we gave the proof of the first part and the proof of the second part. These are nothing but actually the standard facts about directional derivatives and Leibniz rule. And okay, so today, as a corollary of this, we have the following. So here we had in this theorem, we have just two tangent vectors at a fixed point P. But what we can do, we may take P as a parameter and consider a vector field. In that case, these objects will not be just some numbers, but they will be also functions. So let me just talk about that. Now, if V and W are vector fields, and okay, F and G are functions on R3. A, B are real numbers. Then we have the following. We may apply the linear combination of this object to a function. So H is also a function, F, G, and H. Okay. And the second one is this, AF plus BG. Here, you know, we have basically the same statement, right? The only thing is that we don't have P here. So we regard this gadget as a function of P, okay? As a function of P. And the third one is V of this is just V of F, G plus F of VG. Instead of, you know, giving proof of this, actually just these proofs are enough. I'll just explain this on some examples, okay? Efendim? First one, yeah, you're right. The difference between this one and this one, here we have just two numbers, and we are at the point P. Over there, what we have is that this P changes, okay, can change, and these numbers can change according to P. Therefore, instead of numbers A and B, I can just consider them as functions of P, okay? So if you are at a point, when I put P here, okay, I have f of P, g of P, and now these are numbers like A and B, okay? But here, we just consider them as functions, okay? So these are just numbers, but functions. In other words, this theorem corollary is just the parameterized version of the theorem, okay? Instead of working at a fixed point P, we just let the point P vary, okay? So we get the parameterized version, nothing else. Now, let me explain this on some example, you know, how this gadgets work. So we are in R3, I have three functions. Let me say f of x is just, f of x, y, z is just, let's say, just the function x times y. G, x, y, z is the function e to the power z, okay? And h is some function, okay? Let's, for example, consider, and okay, I have to tell you what V and W are. V is a vector field, So at any point, this should give me a vector. So at the point, let's say X, Y, Z, okay? What is this vector? It will be a vector in R3. Suppose it is this vector. X coordinate is constant. And then I have, let's say, Y here, or, okay, X here. And then, okay, Y times Z. And then this vector will be applied at which point? At the point X, Y, Z. So this is my P, okay? X, Y, Z. And W is another vector, X, Y, Z. And suppose it is this one. Suppose it's a constant vector, okay? Constant vector, -1, 0, 5 at the point X, Y, Z. Okay, at the point X, Y, Z. Now, what about this object? F times V plus G times W. Okay, now I have this function times this vector. So X times Y is multiplied with this vector, of course, right? How do we multiply a constant with a tangent vector? Remember from last time, this is nothing but A times V. I multiply the vector part. I don't change the point of application because TPR3 is the vector space, right? And similarly, if I add two vectors, I just add the vector parts. I don't change the point of application. I am always at this space, okay? So if I do this, I will multiply this function with this vector. This is like a scalar multiplied with this vector. So we get what? 2xy, x squared y, x, y squared z at the point x, y, z, okay, plus g times w, g times w, I multiply this function with this vector. So we get minus e to the power z, and then 0 and 5 e to the power z, and at the point x, y, z. Okay? And what will be the result? Result will be, okay, so let me write. Now I will add these two tangent vectors. We keep the point part fixed. We just add the vector parts. So it is just 2xy minus e to the power z, and then x squared y plus 0, and then x y squared z plus 5 times e to the power z at the point x, y, z. Okay, so this is my vector. F, sorry, not vector. This is a vector field. F times V plus G times W vector. All right, so it is this vector. And then we would like to apply this vector to a function H. Let's do that. Şurada sileyim, ondan sonra şey yapayım. İkiydi değil mi o? Okay. All right. Okay, so I would like to compute what? I would like to compute F times V plus G times W at H. So let me write down the vector. 2xy eksi e üzeri z, 2xy eksi e üzeri z, x kare y, ondan sonra da xy kare z artı 5 e üzeri z. xy kare z artı 5 e üzeri z. Now this vector at the point x, y, z will be applied to some other function h. Okay, how would you do this? Yeah, at this point, yeah. Sorry, in this direction at this point. Okay, so just to avoid confusion, let me just, write it like this. Suppose, this is just some V1, V2, and V3, okay? V3. So what is this? This is just the directional derivative of f d dt, of h, at which point? At the point x, y, z plus t times v1, v2, v3. at the point 0. Okay. So what would be the result? The result would be just the derivative of h with respect to first coordinate times the vector part here. So it would be just this, v1 times h sub x at the point x, y, z, right? From advanced calculus, right? If I take directional derivative of f at the point x, y, z along this direction, this would be the result, plus v2 times h sub y x, y, z, plus v3 times h sub z x, y, z. Okay? But what is v1, v2, v3? They are actually functions also. Since I am taking the derivative at a fixed point here, I may regard these gadgets as constants, but then we just vary the point. Therefore, actually, it is not a constant. You know, they are functions. So v1 was 2xy minus e to the power z times h sub x plus h sub x at the point x, y, z, of course. If you want, let me just write that way. And then v2, x square y times h sub y x, y, z plus x y squared z plus 5 times e to the power z times h sub z x, y, z. Okay. Application of a vector, tangent vector at a point to a function is a real number. This is a real number. But application of a vector field to a function is a function. If you evaluate this at a point, at a given point, of course, this would be just a real number, okay? Yeah, sure. This is nothing but, yes. This gadget is just the dot product of V1, V2, V3, and then gradient of H, right? So this is the same thing, okay? Because directional derivative, right, is just the gradient vector times the vector you take the derivative, right, along which. Okay. Sorusu olan var mı? I, switch the variables here at this stage. Otherwise, you may easily get confused. Okay. So far, actually, you haven't learned anything, right? We just renamed what you learned in advanced calculus, right? We gave them some fancy names. That's it. Okay. Now, the next section is so-called curves in R3. So we will study curves in R3. But first, let's see what's a curve in R3. Okay. A curve in R3 is a differentiable function alpha from some interval into R3 from an open interval I into R3. Okay. So a curve is a function, okay, is not its image. Usually when we talk about curves in the plane or in the space, we think of the image of the function, okay? We consider something like this. This is a curve. But technically, actually, this is not a curve. A curve is a function, okay? This might be the image of a curve. But different functions may have different, may have the same image. It doesn't mean that those functions or curves are the same. Okay, they are the same if only if functions are the same. Their images could be the same, but as functions, they might be different objects, and we will consider them as different curves. Let's do some examples. Sorry? Yeah. It can be any interval as long as it is open. First one is straight line. Okay, now let P and Q be points in R3. Then this is a, so I take my interval R minus infinity plus infinity. It's an open interval into R3. And it's given like this. So it is P plus TQ. Okay, so what is this? This is nothing but the a parameterization of the line joining P and Q, right? This is the point alpha 0, right? At t equals 0, I am at this point, and at which point I have this. So I want this to be Q. So okay, 1 minus T Q equals P. Oh yeah, you're. This is not the line joining P and Q, right? Yeah, okay. This is alpha 1. Okay. If you want the line joining, let's say 1 prime. Okay, that was 4. Yes, 1 prime. If you want a parameterization of the line joining P and Q, then you may consider this function. So it is TP plus 1 minus TQ. Okay. So when you plug 0, you are at the point Q, and when you plug 1, you are at the point P. So this line goes this way, right? At 0, you are at this point, and at t equals 1, you are at this point. This is one parameterization for this line, actually. But note that the function beta from R into R3 given by, look at this function, beta t q plus 1 minus tp, okay, has the same image. Right? This is also the line joining P and Q. But this time, so P is here, Q is here. This is beta 0, and this is beta 1, right? So we have two different functions parameterizing the same, actually, line in R3, the line joining P and Q. These objects have the same image, but as curves, they are different, okay? Because their expressions are different. They are different functions. So they have the same image. However, as curves, curve is nothing but a function. They are different, okay? They are different. Okay. So we shouldn't confuse a function with its image, okay? Functions may be different, but their images, might be the same. Still, we will regard them as different curves. Okay. Another one is helix. Okay, so here is our curve, again defined on the whole real line from R into R3, given by alpha t, a times cosine t plus b times sine, no, still a times sine t, and then I have bt, where a and b are positive constants. No, they are real numbers. A is positive and b is different than 0. So what is this? This is nothing but the following. If I didn't have this bt, this would be a parameterization for a circle in the plane centered at the origin with radius a. But here I have this bt coordinate in the z direction. This means as time passes, your circle, gets higher, right? And as t goes to, in the negative direction, then it will go down. So it's a circle, but it is going up and down. So it's a helix, okay? So something like this. And maybe I can stop at this point. So it goes, of course, till infinity in both directions. And in the XY plane, okay, in the XY plane, so this is the Z axis. No, I should cross this. Okay. And then x-axis, y-axis, and this is the z-axis. And the projection of this helix onto the xy plane is this circle, okay? Is the circle in the plane. Well, this is supposed to be a circle of radius a, okay? This is the projection of this helix onto the xy plane. Okay. Okay. Burada 5 dakikam var. Another example of a curve is this, given by e to the power t, e to the power minus t, and square root of 2 times t. I will not bother to draw this. You know, you can just take some points and you know, plot some points and try to see how it looks like. But it's a curve. So for us, a curve is nothing but a function, differentiable function. Okay. Another one is this one. Again, it may not be easy to, you know, sketch the curve. 3t minus t cubed, 3t squared, 3t plus t cubed. Okay. Okay. These are just some curves. Let me tell you the following. We will, of course, mostly deal with, you know, curves where the coordinate functions are either, you know, linear ones or polynomials, exponential, trigonometric ones, and so on. Although, you know, they look like easy objects, you know, just a couple of functions, they are not understood, okay, fully. Even if these are just only polynomials, they are not understood fully. There are a lot of mathematics in this. Especially if you have polynomials here, then these are called algebraic curves. And algebraic curves is a you know, huge subject. We have, you know, we know a lot of things, but we don't know everything. Even very, you know, simple looking questions do not have an answer yet. And Jait Arf has a work on this kind of curves, about singularities of this kind of curves. His work is known as Arf rings and Arf closures. So it's about singularities of this kind of objects. What we mean by singularities, I told you we are dealing with differentiable curves, and we will consider so-called smooth curves where you can always put a tangent vector, okay? A curve, for example, like this, you have always a tangent vector. But there are curves like this where you don't have a tangent vector, okay? Such things are called singularities, and when your object is algebraic, then the singularities can be understood algebraically, and this is what actually Arf's work is about. Of course, there's a huge literature about singularities. I mean, Arf's work is one of them, but Arf rings and Arf closures is about this kind of stuff. Okay. All right. Okay, let me stop here. It is 29. After the break, we will continue.